Hey everyone! So a few months ago, I posted this system design challenge, Challenge 1, and I saw a lot of you in the comments asking for a deep dive into how you'd actually solve it. This is my first attempt at really breaking that down. I should mention up front, this isn't exactly a hello world or a beginner-friendly type of video. We're going to be getting pretty deep into the weeds of distributed systems and data consistency. So you might need to do a bit of outside reading to fully grok some of the mechanics we'll talk about here. But as always, I'll try to build up the intuition from first principles. Okay, so let's look at the setup again for those who missed it. The problem is basically this. You have a monolith. It's sitting on top of a massive 50 terabyte Oracle database, and it's taking 100,000 writes per second, 100K RPS. That is a lot of pressure. It's high velocity state. And the task is to migrate this whole architecture over to microservices with zero downtime and absolutely zero data loss. It's a classic problem, but at this scale, the physics of it get really interesting. So let's get into it. So let's deconstruct this. I want to look at the physics first. If you're a junior engineer, or maybe you just haven't worked at this scale, your first instinct might be, okay, let's just take a database dump. We'll pause the app for a bit, restore the dump to the new DB, and point the app there. Let's do the math on that. 50 terabytes. Even if you have an insanely fast 10 gigabit connection dedicated entirely to this transfer, and you can somehow saturate it perfectly, which you can't because of disk I/O overhead, transferring 50 TB takes like 11 or 12 hours. But remember the 100,000 writes per second. If you pause for 12 hours, you are dropping, let's see, 100K times 60 seconds times 60 minutes times 12. That's roughly 43 billion writes. That is not zero downtime. That is company bankruptcy. So okay, offline migration is out. It's impossible. We have to do this online. The next naive idea, and I see this a lot, is let's just code the app to write to both databases at the same time. Dual writes. This is a trap. It's a huge trap. It brings us to the two generals problem. Basically, you can't have a distributed transaction without a coordinator, and even then, it's slow. What happens if the write to Oracle succeeds, but the write to the new DB fails? Now you're out of sync. What if the network blips for 100 milliseconds? At 100K writes a second, you just piled up 10,000 failed requests in a buffer somewhere. At this scale, application-level dual writes they're basically a suicide mission. You introduce latency, you introduce consistency bugs, and you make the monolith even more brittle. So we need a better way. We need to decouple the event of the write from the replication of the data. And to do that, we have to go back to first principles. We have to ask, what is a database really? If you read J. Kreps's paper on the log, and you really should, it's a classic, you realize that the table, the thing you query with SQL, is just a derivative view. The source of truth is the transaction log. In Oracle, they call it the redo log. In Postgres, it's the wait-ahead log, or WAL. Every time you do those 100K writes, the database is just appending them to a file on disk. Insert X, update Y, delete Z. It's a stream, and that stream is the key to our whole strategy. We're going to use three main components: the Strangler Fig pattern, change data capture, or CDC, and shadow mode. Let's get into the mechanics of moving that 50 TB while the world is still turning. Okay, so how do we actually move the data? We're going to build a change data capture pipeline. Think of it like a hook into the heartbeat of the database. We'll use a tool like Debezium. What Debezium does is actually pretty clever. It doesn't query the database like a normal user. That would be too slow and would kill performance. Instead, it pretends to be a replica. It reads that low-level Oracle redo log we just talked about. So here's the flow. The Oracle DB takes the hit of the 100K writes. It's doing its thing, being ACID compliant. Debezium is tailing that log. It sees every single change. It converts those binary log entries into JSON or Avro events. And then, and this is the crucial part, we push those events into Apache Kafka. Why Kafka? Why not go straight to the new microservice? Well, at 100K writes per second, if your new microservice has a tiny bug or if it needs to restart and you're pushing directly to it, you're going to drop data or crash the source. Kafka acts as a massive buffer. It can absorb that 100K RPS pressure and just hold it. It's a durable stream. But wait, we still have the 50 terabytes of old data. The log only has the new stuff. This is where the snapshotting magic happens. Debezium has this mode where it can do an initial snapshot. It starts reading the existing tables chunk by chunk, while at the same time keeping track of where it is in the log. Imagine it like this. We start the snapshot at time 0. It's going to take days to copy 50 terabytes. While we're copying, the 100K writes per second are still coming in. Those writes are being stored in Kafka. When the snapshot finally finishes at, say, time 100, the new database has the base data, but it's 100 hours stale. But we have the buffer. The new microservice just starts reading from Kafka at the exact point where the snapshot started. It replays history. It eventually catches up to now. Now you have a clone of your 50 terabytes dataset that is only maybe 500 milliseconds behind the master. Let me zoom in on one detail here: concurrency. At 100K writes, you can't just have one process reading Kafka. It's too slow. You need to partition your Kafka topics. But you have to be careful. If you have user A updating their profile and then changing their password, those two events must stay in order. So you partition by user ID. All events for user 123 go to partition 7. All events for user 456 go to partition 8. This way, you can have 100 different consumers working in parallel, but for any single user, the updates are processed in the exact order they happened in Oracle. This is how you scale the throughput without breaking the logic. And one last thing on this: idempotency. The network is unreliable. Kafka might deliver the same message twice. Your new microservice database writes must be idempotent. If you get the message set balance to 50 twice, it's fine. But if you get subtract 10 from balance twice, you're in trouble. So we try to pass state, the whole row, rather than deltas, the math, whenever we can. Okay, so the data is moving. The second engine is spinning. Now we need to move the passengers.
So we have the data flowing, but 100% of our users are still hitting the monolith. This is where we use the Strangler Fig pattern. In nature, a Strangler Fig grows around a tree until the original tree eventually dies and you're left with just the fig. In software, we do this with a proxy. We put something like Envoy or NGX in front of the monolith. At first, it just passes everything through. Then we build our new microservice. Let's say it's the user profile service. We don't just switch over. That's too risky. Instead, we use shadow traffic. The proxy sends the request to the monolith, returns the answer to the user, but also sends a copy of that request to the new microservice asynchronously. This lets us do two things. One, we see if the new service can actually handle the 100K RPS. Two, we compare the results. If the monolith says balance is 50 and the microservice says balance is 0, we know our CDC pipeline or our logic is broken, and we find that out without affecting a single real user. Now, eventually, we have to start writing for real. This is the hardest part. Writing is hard because you need a system of record. You can't have two masters for the same user or you get split brain. So we do it incrementally. We use a toggle in the proxy. If user ID ends in 01, send them to the microservice for both reads and writes. Everyone else stays on the monolith. We move 1% of the users. But here's the gotcha. What if the monolith still needs to read data for that 1% of users? Maybe there's a legacy report or a background job. Now the monolith is looking at stale data in Oracle because the 1% are writing to the new PostgreSDB. This is where it gets a bit gross. You might need a reverse CDC pipeline. You stream changes back from the microservice to the Oracle DB. It feels wrong to write back to the legacy system, but it's a temporary bridge. It keeps the jet engine balanced while you're moving parts. Once you're at 1% and it's stable, you go to 10%, then 50%, then 100%. I want to wrap up by talking about the mindset here. People look at these numbers, 50 terabytes, 100K RPS, and they look for a silver bullet tool, like, oh, just use Snowflake or just use CockroachDB. But tools don't solve this. Engineering solves this. You have to think about data as a stream, not a bucket. You have to design for reversibility. Every step we took can be undone in milliseconds by flipping a proxy flag. And you have to respect Conway's law. You can't migrate a monolithic DB if the whole company is one giant monolithic team. You have to break the ownership down along with the data. So, yeah, CDC, Kafka buffers, Strangler Figs, and incremental migration. That's how you perform the brain transplant while the patient is running. It's complex, it's a lot of infrastructure, but it's how we build robust systems at scale. Anyway, I hope that was a good deconstruction. I'll link some papers on the log and the Strangler pattern in the description. As always, thanks for watching and happy coding!